Anyways, we'll start with third unit, which is design of ALU. So ALU is the heart of the CPU. Simple ALU is considered a combinational circuit. It's a digital circuit to do arithmetic operation using like addition, subtraction, and multiplications, and logical operations like and data movement operations such as load or store. So the ALU must have capability to execute the instructions of LSA. Modern CPUs have multiple ALU to improve efficiency. So ALU includes the following parameters: instructions of architecture, accumulator, stack, register architecture, register stack architecture, and register memory architecture. So orders are the basic building of ALU. So typically basic orders are half order and full order. Parallel orders are nothing but cascade of full orders. Number of full orders used will depend on the number of bits that is needed to generate a binary number. So ripple carry orders are used when the input sequence is large and it is used to add 2 bit of numbers. Okay. Carry look at an improved version of a ripple carry order. So half order is combination logic circuit with two inputs and two outputs. The half order is designed to add two binary numbers A and B. It's basic building block of our addition of two single bit numbers. Our circuit has two outputs, carry and sum. So this is the carry required order internal circuit. So the sum is A inverse B and the plus A into B inverse plus A inverse B. Carry is A into B. So that is why the sum part is implemented using a XOR gate and carry part is implemented using a NAND gate. Next is full order. Full order is a three input order where A, B, and the carry input also is there. But the output is sum and carry. So the sum part is nothing but A XOR B XOR C. So if you look at this diagram, this is A XOR B. This is XOR C. This generates the sum. Then the carry is A XOR B. This output into C plus, that is plus A into B. So this is the full adder circuit of a full adder circuit. So design of ALE, or arithmetic logic is digital circuit to do arithmetic and logical operation like addition, subtraction, and also and or also. So simple circuit 4-bit block diagram circuit is given here. So this is a 4-bit ALU is combined using 4-bit ALU block. So ripple carry order, typically ripple carry order is serial process. Addition starts by adding least significant bits of addend and addend. The next question bits of addend and addend are added along with carry from the preceding bit. This process is represented the addition of most significant bit is carried. So this like this A0 and B0 is added, and this with the carry A1 and B1 is added, with the carry A2 and B2 is added, A3 and B3 is added with carry. So you get the sum S0, S1, S2, S3 and the carry CL. So carry propagation from the above example, it can be seen that there are adding 3 bits at the time sequentially until all bits are added. The full adder is a combination circuit that performs the addition sum of 3 input bits from the previous order. It results contain the sum and the carry to the next stage. So this is a circuit diagram of a ripple carry adder. So this is how a ripple carry adder works. So we'll see the 4-bit ripple carry adder. This is the internal implementation of 4-bit numerical carry adder. So if you look at it, two inputs A0 and B0 with C0. So the output is C1. So this is the input of the next triple carry adder with B1 and A1 likewise. So and also you get S0 in the first case and S1 in the second case, plus C2 is the input for the third triple carry adder along with A2 and B2. Here you generate S2 and C2, C3, which is the input for B3 and A3, which gives you C4 and S4. So if you look at this case, the fourth output can be generated only after one carry, two carry, three carry is generated. So you have to wait. So to overcome this, we design fast adders. The first fast adder is carry look ahead adder. A carry look ahead adder is a type of adder used in digital logic. Carry lookahead adder improves speed by reducing the amount of time required to determine the carry bits. So we'll see how it is done. So the type of adder circuit is called a carry lookahead adder. A carry will be generated in two cases when both A and B are 1. When one of the bits is 1, the carry is 1. So the figure shows the full adder circuit used to add operands in ith column, naming Ai and Bi and carry bit Ci, for which is coming from. So if you look at the circuit, in this case we have two things, Pi and Gi. Pi is nothing but your propagate and GI is carry. So PI is nothing but AX or B and GI is A into B. So in this circuit, the two internal signals PI and GI are given by AXIB and A into B. The output sum and carry can be termed as a sum is Pi XOR Ci and Ci plus 1. The carry can be said Gi plus Pi Ci. So from the diagram. So with this, Gi is known as carry generate signal since the carry is generated whenever Gi is equal to 1. And Pi is known as carry propagate signal since whenever Pi is 1, the input carry is propagated to the output carry. So computing the values of Pi and only depend on the input bits Ai and Bi as clear from this. We have eradicated Ci in this case. So using that, I can say C1 is equal to G0 plus P0 C0 and C2 is equal to G1 plus P1 G0 plus P1 P0 C0. So if you look at all this thing, you can with C0 alone generate C4 carry. So that is what we have saved 4 clock cycles. This is probably look ahead adder. So this is a small implementation of it. So a 4-bit carry look ahead adder circuit will look something like this. Next is parallel adder and subtractor. So in this, both addition and subtraction is done by a single circuit. So and how it is done? You have a M bit which is called um, the moderator, or so when m is equal to 0, the output of XOR there would be B XOR 0 equal to Bi. If the full adder receives the value of B and the input carry is 0, the circuit performs A plus B. When m is equal to 1, the output of XOR will be B plus XOR Bi plus XOR 1, which is Bi. If the full adder receives the value of B and the input carry is 1, the circuit performs A plus 1 complement of B, which is C plus 1, which is equal to A minus B. Okay. So multiplier, addition, unsigned, signed, fast carry, addition of summons. These are some problems which we are going to see. So the first thing is binary multiplier, unsigned number multiplication, 2-bit n-bit numbers, 2-bit result. So I have two bits B1 and B0 and A1 and A0. So when I multiply A0 B1, A0 B0, A1, B1, A1, B0. I add this, I get C0, C1, and C2 and C2. So this is the circuitry. So basically B1 and B0, A0 is given as input. So A0, B0 is C0, and A0, B1 plus A1, B0 is C1, and this carry is given to the next thing where A1 B1 plus this carry is C2 and C3. This is how you generate a binary multiplier. So this is how the multiplication takes place. So the binary multiplier first partial product is found by multiplying B1 B0 by A0, and second product is done by multiplying it with A1 and shifted one portion to the left. The two partial products are added in two half adders. Usually there are more bits. If there are more bits in the partial product, then it will be necessary to use full adders. Okay, this is a two diagram of binary multiplier. So the least significant bit of the product does not have to go through an adder since it is found by the output of the first output. So multiplication of positive number, shift and add multiplication, we'll see. So this is the circuit thing. So what happens basically is the multiplicand and the product is added to the ALU, and after every addition, the product multiplier and product is shifted to the right one bit. So this is the operations. So 100 into 1, it is multiplied, shifted one bit, then it is multiplied, shifted one bit, then multiplied. And after all the product is done, it is added to get the final result. So how do I do it? When start B is equal to X, Q equal to Y, A equal to 0, and N equal to N. N is the number of bits. If Q naught is equal to 1, A equal to A plus B. That is the last bit of the multiplicand is 0. Then you do A equal to B and shift A. Else you just do a right shift. So that is what we are doing. So check this bit 0. Then I'm shifting it right one bit. So all these values is move to the right one bit. Then I'm checking Q naught bit 0 again. Then I'm doing a right shift. Then I'm shifting to bit 1. So first you add A and B value. Then you do a right shift. Again check 1, add B to A, and so number of steps is done. This is our final answer. Okay. So these are some of the examples. So signed multiplication, for that we use Booth's algorithm. So the Booth's algorithm is something like this. See, in case of normal unsigned multiplication, we check the Q naught bit. Here we check Q naught and Q minus 1 bit. So if Q naught and Q minus 1 bit is 1 and 1 or 0 and 0, then arithmetic right shift will happen. Yeah, anything other than 1 and 1 and 0 and 1, 0 0, if it is 0 1, A equal to A plus M, then arithmetic right shift. If it is 1 and 0, A equal to A minus 12 and arithmetic right shift until count is 0. So this is it. This is our Q naught bit and this is Q minus 1 bit. We check both and 1 0. So A equal to A minus B and arithmetic right shift. Again we check the last two bits, it's 1 and 1. So arithmetic right shift. Next we check last two bits with 0 and 1. So A equal to A plus 1, then arithmetic shift. Now it is both 0 0, so only arithmetic right shift. So take the one, as the leading bit is 1, takes the two ones complement, that's your answer. So this is also same. So check the last two bits, 1 and 0. So A equal to A minus M and shift. Again check the last two bit 1 and 1. So just do a right shift. Then check the last two bits 0 and 1. So A equal to A plus M and do a right shift. So now check 0 and 0. Just do a right shift, which will give you the final answer. So these are some more examples you can practice with that. So alternate method is Booth algorithm. So both multiplication reduces the number of additions, the intermediate result, but sometimes make it worse as we will see it. So to overcome this, we use Booth multiplier recoding table. So how do I recode? So using these values 0 and 1, there is a positive transformation, so 1. So 1 and 1 note on 0, 1 and 1 note on 0, 1 and 1 note on 0, 1 and 0 there is a negative transformation minus 1, then 0 and 0 is 0. So this is, so whatever number is given, you take the multiplier and convert it into Booth's recorded multiplier, then you do the multiplication. So Booth's algorithm, good when you have good multiplier, that is consecutive zeros and ones, good set, then 4 speed, 8 speed improvement will be there. When you have ordinary multipliers, that is 0 minus 1 continue 2 zeros, then plus 1 minus 1 like this, then the speed is it is called ordinary multiplier. Worst case multiplier is alternative zeros and ones. Next, we'll get into next topic, which is bit pair recoding of multipliers and carry save addition of some bands. So these two are fast multiplication category. So in fast multiplication, there are two techniques to speed up. One is bit pair and the other one is fast add and sum. So in bit pair recoding, see in bit recoding, we convert it into if it is a 4-bit number, we convert it to 4-bit numbers. Here in bit pair recoding, it is halved into half. And we take three bits and compare. When it is 000, it is 0. When it is 001, it is 1. 010, it is 1. 011, it is plus 2. And likewise, 100 is minus 2. 101 is minus 1. 110 is minus 1. And 111 is 0. So any number given to us, we recode it like this and then do a multiplication. So how I multiply with minus 2? When I multiply any number with minus 2, I multiply it with 1 0. That's it. What if it is minus 1? Then I do it the 2's complement of that number. And then add it till I get the final answer. This is bit pair recoding of multiplication. In carry save add-ons of someone, what I do, I take three bits and add it and then give the answer. So if you look at this problem, A and B are done, that is multiplication of these two. C and D are multiplication with these two numbers. E and F are multiplication with these two numbers. So what I'll do, I'll add these to A and B. So I'll get S1 and C1. So when I add this, I get the following. So it's something like this, S1 and C1, DEF S2 and C2, S1, C1 and S2. I get S2 and C3. With that I'll add S2. I get S4 and C4, which is my final answer I add. So something like this. Next we'll get into division. Here you have two methods, restoring and non-restoring division. So the first is restoring division. So similar to multiplication circuit, n bit positive divisor is loaded into register 1 and an n bit positive dividend is loaded into register 1. The start of the operation, register A is set to 0 and after the division operation is completed, the n bit quotient is in register Q and the remainder is in register A. The required subtraction is facilitated by using 2's complement. The extra bit at the left end of both A and B accompanies the sign bit during subtraction. So this is the circuit we got. So this is the flowchart for restoring division. A is set to 0, M divisor, Q dividend and count is M. Shift left A and Q, then do A equal to M minus 1. If A is less than 0, Q naught will be set to 1. Otherwise, Q naught is set to 0 and A equal to A plus 1 is done and count is minus until this operation happens until count is 0. So that is what happens here. So here what you do, you check the Q naught bit. If it is done, you restore it, else you don't restore it. In non-restoring division, initially dependent is loaded into register Q and the m-bit divisor is loaded into register M. Let's M is 2's complement of M. Register A to 0, set count to M. Shift AQ denotes shift left AQ by one position, leaving Q naught blank. Similarly, a square symbol in Q naught position denote it is calculated later. So this is the thing. So the algorithm is set A naught to 0, default enter, if sign is positive, shift A Q left and subtract M, set Q naught to 1, else if sign is negative, shift A into and add M to set Q naught to 1. If the sign of A is 1, add M to A to U. So this is how I am checking the sign. First I am shifting, then subtracting A minus M, then setting Q naught with the leading bit. Now I am checking the sign of it, then shift and add, then Q naught to last bit, shift, add after signing the bit, and this operation until n becomes 0. Last is floating point numbers and operations. So here we have the IEEE 754 standard for dealing with floating point arithmetic. So what we do here is IEEE 745 has three basic components. Sign of the matrix are 0 if it is positive and 1 if it is negative. The bias component, the exponential field, needs to represent both positive and negative numbers. Normalized mantissa, the mantissa is part of number in scientific notation or floating point number. So simple precision it is 32 bits, sign is 1 bit, exponent is 8 bit and mantissa is 23 bits, whereas double precision 64 bits, sign 1, 11 bits for the exponent and mantissa 52 bits. So single precision bias exponent is 127 plus 6, whatever number is given, that is 133. I convert it into binary. Normalized mantissa is this. So we'll add 0 to complete the 23 bits. So the IEEE 7 single precision is 0, the 123 and the mantissa part. For double precision, biased exponent is 1023 plus 6. So for that I'll convert it into the binary digit. Normalized mantissa is 01010. We add zeros to complete the 52 bits. So this is the double precision. So IEEE has reserved some values that can be ambiguity. So 0 is special value denoted with an exponent and mantissa of 0. Minus 0 and plus 0 are distinct values, though both are equal. Denormalized if the exponent is all zeros but mantissa is not, then the value is denormalized. So infinity, the value of plus and infinity are denoted with all exponent of all ones and a mantissa of all zeros. So this is simple precision. So the range of floating point numbers are negative numbers less than 2 minus 2 to 3 into 2.27 and negative numbers greater than 2 to 149 is negative underflow and 0 positive numbers are less than 2 to 149 is positive overflow and positive numbers greater than 2 to are a positive overflows. So single precision is plus or minus 2 to the power minus 23 into 2 to the power 127. So in the approximately 10 to the power 38.53. Whereas double precision is 10 to the power 308.25. So with this, thank you. Second unit is done.